Welcome to the Tomotherapy and Radixact log analysis training session. In this training, we're going to identify the stages of gantry initialization and the tasks that occur during the individual stages for both Tomotherapy and Radixact. We're also going to use the log view plugin of ISTT to look at different error messages in the logs and ways to find troubleshooting documents using SecureSync. This slide here shows you that just a quick outline of the different states comparing Tomotherapy to the Radixact machine. We'll go through each one of these in great detail in the following slides, but the point here is to show you that while Tomotherapy is sort of a complete basic flow chart, Radixact's a little more complicated, has a few extra states and some other items going on at the same time. So jumping into the Tomotherapy, each subsystem must successfully report for a state to transition to the next state. A list of all subsystems is given at the beginning of the logs. I'll show an example of that in the next slide. Expecting 15 subsystems to register. Each subsystem reports finished for every state, even if it does nothing for that state. So here's an example on the left here of what the logs will look like. And you will see this in the beginning of the logs after the machine starts up. So the task registers at boot up must confirm completion in each state, even like I said before, even if they don't have anything for that state and for that condition. Which tasks are required is determined by system configuration. So this one here is something that people get confused on sometimes. The last two states report finished. You'll see a log message that says they're not finished. A lot of times that you confuse thinking that's a problem because they haven't finished, but that's part of just normal operation. Okay, so jumping into these different states for Tomotherapy, pre and net. In this state, the treatment system is powered on. Software does MD5 checks. The computer's time sync. Subsystems register with the state coordinator. Jaw, gantry drive, and couch type, etc. are installed or identified. Watchdog task is started, and the DCS parameters are logged. The HP couch and Galil or Mint drive calibration data is logged. In the init state, JAWS, couch, and gantry drive types installed are verified and logged. MLC initializes running self-test. Gantry initializes. The PCPs connect and initialize. JAWS initialize. Lasers initialize. In the idle state, the system is waiting for the user to select a procedure for treatment. The gateway switch interface connects for the legacy Tomo, and it's connection made to gateway legacy Tomo. In clinical, again, only used when the system's in clinical mode. All subsystems report. Obviously, this clinical mode is when the service laptop's not connected in service mode. Setup prep, run self-test of the MLCs. That's up by internal utilities to monitor MLC subsystem operation. Procedure data, jaw position, couch position, trigger rate, procedure length, etc. loads from the database server. Stats console key must be in program in this state. Lasers move to home position. The software takes control of the beamline. And Tomo gateway switch interface returns connection disabled. And wait for setup, the AOM values are loaded. Ready button must be pressed. Setup button can be pressed. Lasers move to position for treatment. Stats console begins to wait for the key to go to image retreat. JAWS move to correct location. Gantry speed is verified for helical and position verified for Tomo direct or static procedures. And the software is waiting for the interlock to close. In start prep, stats console key must move to image retreat. SCS STC now detects safety interlock to be closed, and all the tasks signal ready for radiation. In wait for start, safety interlocks detected to be closed on the OBC. All relevant tasks signal ready for radiation state, and the user presses the start button on the status console. Fragment begin. Tomodirect procedures will have between 2 and 12 fragments. Helical procedures have only 1 fragment. Radiation prep. All required subsystems confirm completion, and gantry speed or position is verified. In radiation, ring data transfer, high speed via hotlink begins. Radiation is delivered. During radiation, RDS monitors machine status, including gantry speed, position, couch speed, position, jaw position, MLC leaf position, modulation, Linac trigger, count, tick mode, status, hotlink errors, DCS performance, etc. In fragment complete, software determines if another fragment is to be delivered as defined in the procedure. If the answer is no, it goes to post-processing. The gantry rotation stops, jaws home, and stats are logged. Final couch position is logged. In the save data state, status console key moves back to program. Data saved to the DRS or the SCS and data server. Treatment system prepares to move to idle state, and the gateway switch connection is enabled. So that's the normal flow, no errors. If errors happen, it has a different way of handling things. And the way it handles stuff is based on the severities shown below. You have normal system events, RD information. RD recoverable is a component experienced an error that it can correct without a restart by just maybe answering the assist and continuing. Unrecoverable hard would be a hardware component has failed and it takes the user to reboot the system to get it to recover. And an unrecoverable soft would be a software issue that requires a reboot. Okay, so that's the tomotherapy flow. For the Radixact machines, the software ensures coordinated procedure delivery by transitioning software units through states. So this diagram here on the right shows that. Maybe zoom in just a bit. We'll go through it in detail to make it a little more sense here. We divide the different states into 4 different groups. We have machine down here, encounter, procedure, and fragment. Similar to the tomotherapy, it runs through those states, but as you'll see, it moves from one group to the next as it goes. So we'll go through them here in a sec. So in machine state, in the machine group, there's 5 states. Startup, init, wait for encounter, post machine, and wait for power off. In startup, the software is waiting for the first state that I'm sorry about that. The first state that all software state participants enter is the startup state. In this state, participants determine the state of the hardware. The software waits for a connection from the TDCS. In the init state, the software item is connected to the TDCS. All applications are registered. Each software unit will perform their respective initialization routine. So all this part of it is in the init is almost identical to what the tomotherapy init state does. If the system did not shut down properly during the last procedure of the previous power cycle, the software item then attempts to recover that procedure. In wait for encounter, the software units have completed their initialization routine, and the ECS and TDCS are waiting for the operator to start a patient session or to power off the system. This state will be post-machine will be reached after a fault or the TDCS closes. Procedures can no longer be run in post-machine. Wait for power off. The system is about to be powered off. Any remaining data or log messages should be written to disk before the PDU key is turned. Okay, so now the next state is encounter. In this state, the ECS ensures, or excuse me, in this grouping, the ECS ensures coordination procedures delivered by transitioning software units through the states. All right, so for the very first state in encounter is clinical mode. So again, it's similar to tomotherapy. If the laptop's not in service mode and connected, you'll be in clinical mode. Prepare encounter. It's waiting for the user to load a patient on the TDCS, and the ECS will display the patient info when the PCPs and move the lasers to the proper position. Applications receive encounter information. And wait for procedure. Obviously, the system is waiting for the user to load a procedure for the selected patient. In post-encounter, patient information is removed from the PCPs. The next grouping here is procedure. And wait for ready under the procedure group. The ECS is waiting for the user to position the couch and press the ready button on the PCPs. Once the ready button is pressed, the couch will start moving to the ready position. Applications receive necessary procedure information. And wait for interlock. The ECS is waiting for the entrance door of the the treatment room to be closed and the status console key to be turned to either image or treat. And wait for start. The ECS is waiting for the user to press the start button on the status console and the interlocks are closed. And wait for fragment. The ECS is waiting for the TDCS to select and load a fragment. The interlocks are still closed. And post-procedure, the detector measurements are completed. Procedure stats, including beamline, jaw, ox monitoring, and network stats are generated and logged. The ECS outputs procedure information to the ECS results file, and procedure return data is collected and sent to the TDCS. The last state, or second to the last state we're going to talk about, a group we're going to talk about is fragment. In prepare fragment, applications receive information about the fragment to deliver. Time-based information is relative to the delivery. All ECS software has completed their initial checks in preparation for radiation beam on. Applications notify the delivery plan manager of the time they need to start fragment delivery. The interlocks are still closed. And wait for soft start. The ECS is waiting for the TDC to send a soft start signal. When the signal is received, the system start time for the fragment is calculated based on the time the soft start is received from the maximum time returned by applications and prepare fragment. In radiate prep, the system start time is distributed to the applications. The interlocks are closed. In radiate, the ECS delivers and monitors radiation. All applications begin executing their portion of the fragment at the system start time. In post-fragment, the planned radiation of current fragment has been delivered. Fragment stats are generated and logged. The couch has been commanded to stop. Add fragment results to procedure return data. The interlocks are closed. The last grouping that we're going to talk about here is the fault type, fault action, if you will. Fault behavior depends on the current state and type of fault. All fault states must take steps to prevent radiation generation and delivery. In the fragment fault state, the interlock is kept closed. and exactly the same information as what we talked about with the tomotherapy errors. Okay, so now for a couple examples of errors in the logs. So over here on the left, but for Radixact logs, or even tomotherapy logs, but specific, I mean, for absolutely necessary for Radixact logs, very first thing I do when I open a log is I go to log, filter, and the filter will pop up this window, and I'll go down here and say show all entries. In the Radixact logs, they had what's called, they won't show verbose information. They consider it's, maybe not something the user needs to see all the time. But for analyzing the logs, there's information in that verbose, or information that's considered verbose that is useful for us. So I always tell it to show all entries. The next thing I do is I will open Procedure Browser, and I'll find the event of interest, and I'll go to that error. If a procedure wasn't started, and this happened if an error happened during initialization, the procedure browser may not show that, so you'll have to go to that boot up, which is the beginning of the new state coordinator. So in this example here, we're going to go look at this DCS hardware not detected error. So I highlight it and say go to error. It pops up and it shows that the error message, hardware not detected, out of range. Scroll up or down, you'll find some more details. It tells you that it's only 2.9 volts, with expecting it to be 540 to 660. And then another really super important piece of this ET send fire event will always tell you who fired the shutdown. So you're not confused by when you see jaw errors after a shutdown happens. You can actually look at this event and see, well, this line in the code, in the logs, and see who actually fired the shutdown. So I don't show them here, but further down in the logs, they're jaw messages because they're responding to, they had started an operation. The event, the Linac fired a shutdown event. The jaws couldn't finish the operation they'd started, so they throw an error message. So you can ignore those when you see that the Linac is the one who fired it first. So carrying it on to the other training about log analysis or using Secure Sync, there's a couple ways that you could find what you should do next. You could just go to the DCS filter and look through there. Oh, look, we have a troubleshooting document. Or you could go to the troubleshooting folder and do the same thing and see that we have one for DCS. And if you open up the troubleshooting document, see, look, there is a section for power supply voltage out of range, and then you would just follow those steps. Here's another example where we have a MLC error. Again, MLC fired cancel, final leaf position fault. You scroll down, you see that you have a leaf error 4 has a problem. You confirm that there's no other thing. Here's your ET send fire event. The MLC fired the shutdown. Same thing again, using Secure Sync. You can see we have a troubleshooting document for MLCs. And we have quite a extensive flowchart for troubleshooting MLC faults, position faults, activation faults, etc. Here's another example. Just this side over here, this data here on the left-hand side is just, again, saying show all entries for Radixact. We have a jaw fault error, it appears. So we go to that error and we look at it, and yep, we can see the jaws did fire the event. We have this error code, it says glial axis error, that gives us this hexadecimal number. We can also So this is an example here. Let me back up a little bit. So you go to error, it brings you to this line here. And you see this 2783115 error code. So you either scroll up or down. In this case, you're scrolling back up, and you find that error code with the stars around it, and it gives you this hexadecimal number I was talking about. So again, you see we have a JAWS troubleshooting document. You go to that JAWS troubleshooting document, and it tells you how to decode, if you will, that hexadecimal number into a binary number, and then it gives you what bit is set, and then you find that bit, and it gives you things that you can do, what the description of the error is, possible cause, and possible resolutions. Here's another example where there's a KV fault. These aren't as clean with the error codes as what I just showed you before. You know, they don't have like this 9-digit number, but in this case, you have to go from the verbiage, which tends to be a little more descriptive than what we've seen in the past. So we got to this point the same way, procedure browser, and then we went to that procedure fault when it showed up. So in this case, you have the generate exceeds output error. And once again, sorry to sound like a broken record, but just pointing out the access that everyone in the field has to the troubleshooting documents and ways to find them. You have troubleshooting the KV subsystem. And there's a section in there for what to do for exceeds output. In this case, it was a firmware issue with pre 4.2 firmware. And when you add this, if you update to this firmware, it greatly reduces the occurrence of it. It doesn't completely eliminate it, but it greatly reduces it. So this may be the last example, or maybe one more. So here's another example of a KV generator fault. I think it was this one and one more, sorry. So in this case, same thing, you know, no really super coding here. You have to look through the logs and you see that you have the generator fault, the generator fired the shutdown. Yeah, you really don't know why. There's not any details in here. So in this case, you would go to troubleshooting documents. I have go back to the 1161 document, troubleshooting that. It would tell you to pull the logs and look at the time sync error messages in the RDS logs compared to the generator logs, and you see in this case there's a lot of rotary faults. We don't show it. I didn't show an example here of the section in the troubleshooting document, but there is a section that goes through pretty good detail of determining if it's the rotary controller board or cabling, or if it's possibly arcing that's causing the rotary faults. And the last example here is a Scandinavia interlock fulfillment current error. And in this example, we're showing the use the GUI to look to see what interlock is being tripped, and then we list here a few items that it could be. Normally, when we've seen this in the field, it's been a cabling, and we point out the cables, possible cables that could be. And that concludes this training. Are there any, if you have any questions, you can email support about it. Otherwise, I hope you have a good day.